For nearly a century, the historical view of our solar system ended in a cold, static graveyard. Looking past Neptune meant looking into a void where planetary evolution was assumed to have stopped billions of years ago. This led to the dropped blanket theory. Models predicted that as Pluto reached its furthest point from the Sun, its thin atmosphere would completely freeze and collapse onto the surface as a solid layer of frost. Data from the New Horizons probe and the James Webb Space Telescope has completely replaced those old assumptions with something far more complex. The instruments detected migrating ice caps, subterranean volcanoes erupting icy lava, and a nitrogen atmosphere that is actively leaking into the void. The edge of our solar system is a remarkably active, breathing ecosystem. This discovery leaves us with a central mystery. How does a world this far from the Sun find the energy to stay geologically alive? Pluto's activities starts with its extreme tilt. Unlike Earth's moderate lean, Pluto sits at 122 degrees, nearly sideways relative to its orbit. This orientation creates bizarre polar days and nights, lasting 124 Earth years. For over a century, one hemisphere receives zero solar radiation. When sunlight finally hits that frozen side, it triggers a rapid sublimation process. Volatile ices like nitrogen and methane absorb enough energy to jump directly from solids into a gas. This massive release of vapor thickens the sky, causing the atmospheric pressure to spike by up to 4 times its normal density. This gas migrates across the dwarf planet toward the colder, dark side, eventually freezing back into ice on the night-shrouded surface. This century-long migration of ice means Pluto is constantly resurfacing itself. It functions as a massive climate engine, driven by its own extreme orbital geometry. Rising above the surface, the James Webb Space Telescope recently analyzed a complex, high-altitude haze layer that controls Pluto's energy balance. This haze layer cools the atmosphere while simultaneously absorbing extreme ultraviolet light from the distant Sun. Absorbed UV energy gives methane molecules the kinetic kick to escape Pluto's weak gravity. 50,000 billion molecules stream into space every second. Pluto's moon Charon acts as a catcher's mitt, intercepting this escaping methane and painting its poles red with organic chemistry. Charon has its own chemistry too. JWST detected carbon dioxide and hydrogen peroxide on the surface, suggesting active cratering is exposing materials from its interior. This physical exchange of material connects the two bodies into a single binary system, sharing chemistry across the vacuum. The activity also comes from below. Deep in the Hayabusa Terra region lies the Kilatse caldera, a massive collapse feature. Kilatse is a cryovolcano that erupted icy lava within the last few million years, fueled by internal radiogenic heat or ancient tidal friction. This dynamism extends past Pluto and into the wider Kuiper Belt, as recorded by the New Horizons Student Dust Counter. The probe is detecting high levels of dust far past the expected edge of the belt. These readings suggest the boundary of our solar system's debris field extends to 80 AU or more. This dust provides evidence that the Kuiper Belt is a violently active region, filled with colliding comets and asteroids constantly grinding each other down. Our old model of a dead outer zone is now obsolete. We see a dynamic binary pair with its own climate cycles, atmospheric exchange, and internal heat, all sitting within a violently colliding disk of debris. Distance from a host star doesn't prevent complex geological activity. Pluto proves internal heat and extreme orbits drive evolution billions of miles away. This rewrites the rules for where complex chemistry can survive, expanding the regions where we might search for the building blocks of life. These dynamic, evolving worlds are hiding in plain sight at the edge of our Sun's reach.